Hello everybody, hope you're having a good day today. And today we're going to be doing part 4 of the kinematic series, and we're going to be going over kinematics graphs. So essentially displacement versus time graphs, velocity versus time graphs, and acceleration versus time graphs. And these graphs are pretty important on the AP tests and the multiple choice sections, and also sometimes in the FRQ sections, but it's also a really good skill to know because it's going to help you create a lot of inferences and problems when problem solving, and it's also going to give you a clear understanding of the concepts in kinematics. So I hope you're excited, and let's get to it. Alright, so let's just jump straight into it. So first graph let's talk about is the displacement versus time graph, or in this case I wrote here x versus t, and that's essentially just like if you remember from last video, and that last video is about like kinematics equation. So if you want to check that out, you're going to need them today, so if you want to check that out, go ahead, link will be in the description below, or you can just go to my channel and find it. But essentially, so this is going to be displacement versus time graph, and we know the symbol for displacement is x, or it can also be d, but I have x here, and then versus time. So here in that case, we always put time as it's our independent variable on the x-axis, and our dependent variable, which is x, well, sort of dependent variable on the y-axis. So that's what we did here. So let's say, for example, we had a line like this. So let's say we had a linear line, right, for example. So what this means is, if you just think about it mathematically, right, in a graph in a linear line, we know that the slope is constant, right? And so we know that this object right here, right, so that means that it's like, let's say if we had times here, right, like, so say this was 1 second, 2 second, 3 second, 4 seconds. We know that at every second, at every second, we know that it's changing by the same amount. Its distance or its displacement is changing or increasing in this case by the same amount, and we can see that here, right? If we were to draw lines, this would be the same amount. So what we're essentially saying here is, if we recall that, for example, this might seem like really weird, this example, but if you recall, we remember that velocity was the displacement over time, right? If we recall that, right? So when we're doing slope, right, for example, so when we do slope, what we're doing? We're doing the change in y over the change in x, or let me just write that. So slope, which is denoted by m, usually in math, we're doing the change in y axis, change in x. So in our case, what the slope would be is change in the y-axis, which is actually displacement in our case, right? And you might be seeing what I'm getting to here. So let's say this is our slope, right? So m, and what we see is it's the change in the y-axis variable, which is delta x here, over the change in the x-axis variable, which is time. And you can see that this is the same thing as finding for velocity. So what that essentially is saying is that by finding the slope of a displacement versus time graph, or distance versus time graph, gives us the velocity. So I'm going to write this. So the slope, or m here, is our velocity. So that is our velocity that we're getting. So that means if we were given a question that was like, oh, this person traveled, like, we got a graph and it was like, so they traveled 30 like meters, for example, in 4 seconds, then we could just find the velocity, or the average velocity here. Remember, average velocity is the change in displacement over time, which would just be 30 over 4 seconds, or 30 over 4 meters per second, right? So that means that the slope is the velocity. So now let's talk about the velocity versus time graph. So our velocity here again is the y-axis variable, and the t, again, time, is our x-axis. And also, let me just reiterate, this time's in seconds. It can also be in other like time formulas, but since it's all the variables here are going to be in their standard unit. So now here we come to velocity, and okay, since here we found out, well, let's just use the last example, right? Because all these graphs are actually related. So since the last one we said that our velocity and our displacement versus time was constant, so that means if we think about it in math terms, a line that would be constant would just be something like this, right? So something like that, a straight line, that would be a constant velocity. And so since this is, I'm also going to just like, so this is 4, right, because we had that like last time, and I'm just going to draw a line down here, and it's going to be important later. But so this is our velocity graph, right, just here, of this displacement versus time graph. Getting the information from this displacement versus time graph, we get this velocity versus time graph. So since the velocity is constant, that means that is our velocity. Now, when we do our practice problem today, it's going to be a great example of it, but remember when we were talking about formulas, we had displacement or displacement, right, was velocity versus time if velocity was constant. Well, here in our case, since we're, or not constant, but if velocity was like the average velocity, right? So here in our case, we have the average velocity, right? And if we were to think about it, the area under the curve, right, or in this case, the area under this rectangular piece, this shaded part right here, this tech is essentially just the y-axis variable times the x-axis variable, which is just finding the area of a rectangle, for example. So this would be t, right? If you were to do like just a normal rectangle, right? So this side length would be t, and this side length would be v, right? So that would give us the area of vt, right? That would be the area under the curve. Now, recalling back to what I just said moments ago, that means that the area under the velocity versus time graph, right? So this area right here, the shaded portion, gives us the displacement. So it gives us what we got here. So for example, if our velocity that we found was like 30/4, right, for this example, and 4 seconds, then 30 times 30/4 would just give us 30 meters, which is again what we have here. So that means the area under the velocity versus time graph gives us the displacement of the object, right? So that's just, and now there's more scenarios we're obviously going to go over. This is just a constant velocity scenario, so where like the object's speed is like never changing, right? So it's staying constant, right? So this is just one scenario. There's another scenario that I'll go over, but it's just, let's just get the concept down. This is how it sort of works. So now next, actually, we're going to transition over to acceleration versus time for the same example here. Same example. So since here we see that velocity is constant, we talked about how last time when velocity is constant, that means that your acceleration is 0. So that means our line would just be on the the x-axis, right? So that is our 0 acceleration. So that's essentially the acceleration versus time graph. But now I'm going to go over another example. So I'll just go down here and we'll go over another example here. So let's say we have a displacement versus time graph first, right? And so we got here, we got x, we got t, right? And there's cases where you're going to have a graph like this. So your graph's going to be like a half. It's going to sort of look like a quadratic, essentially, like a half of one, like a parabola, and it'll look like that. And what this is saying is, well, let's just think about it. Let's say since we're saying it's like a quadratic, right? Let's just think about it. That means as your time is increasing, right? So as my time is increasing, so 1, I'm here. At 2, I'm here. At 3, oops, let me write that better. So at 3, oh my god, okay, so okay, I can't draw 3 straight. Okay, at 3, you're here. At 4, you're here. Something like that. And what we're seeing is that the displacement is changing at an increasing rate. Unlike on our previous example where we were changing at a constant rate, so this was all the same. Here we're increasing in a increasing rate. So it's this much here, and now a lot more here. So it's increasing, right? It's an increasing graph. So that means our velocity isn't constant, right? Because since we're increasing, we can't have a constant velocity. We have to be changing velocity because remember, more velocity that we have, the more distance we're going to cover in a certain amount of time. So that means that here, if we were to use calculus, right, and define slope, we could find the slope of this graph. We're not going to use calculus, right, because physics 1 doesn't really need calculus here. We can just use our logic from math, and so that means if we were to transform this into a velocity versus time graph, right, since we're saying it's increasing, right, so every time it has an increasing, so it's basically increasing from the previous rate, so that means this would actually be a line, meaning that this basically is stating that it's increasing every second. So again, let me just write the times out. So 1, just like till 4 seconds, right? So that means we're here at this point, and here at this point. So our velocity is constantly changing, right? And it's increasing, right? Just like this displacement graph where we saw that it was always increasing. Now let's talk about how this relates. So if I were to obviously remember that if we find the area under this curve, we're going to get the displacement, total displacement after 4 seconds. Now, another thing that I did not talk about in the last time, because we had constant velocity, but it also makes sense to the last scenario. Remember that we also found that acceleration was the change in average velocity over time. So again, if we were to find a slope of the velocity versus time graph, which is change over y, change over x, right? So then that would be, again, change of velocity, change over time. So that means that the slope of the velocity versus time graph is also the acceleration, the average acceleration. And again, if I were to go back and check out this example, we know that we found out that our acceleration was 0. But since this graph right here has no change in, it has no slope, right? Because this is just a 0 slope. So that means that it also stays consistent that our acceleration must be 0. So coming back to this point, so we saw that our acceleration is actually a constant acceleration because linear lines, so the slope is always going to be constant. Here, this wasn't linear. The x versus t graph wasn't linear. Therefore, our velocity was not. That's why our velocity was increasing at an increasing rate. So as time increased, our velocity changed. So our velocity increased. So that's why we got a linear line. And like last time, where our displacement was constantly increasing, right, at the same rate. So that means our velocity is just a straight line, constant, right? So it's important to remember the rates and all that stuff because you want to look at, okay, at this rate, an increasing rate or decreasing rate, because sometimes you could get a graph, for example, if this was an x versus time graph, right? So, right, if it was this, you could also get something like this, right? And you got to think about it. So that means you're at a certain point, you already are starting at a certain x value and you're decreasing over time, and your rate of decreasing is increasing, right? And that sounds kind of confusing, but just think about it. Every single second passes by, I was at a certain point, right? And now I'm farther away, further away, further away. So I'm increasingly decreasing, if you think about it that way, or decreasing at a more or extra rate, right? And then like a linear line like this. Because this would just be a constantly decreasing pattern, right? So there are different kinds of graphs that you could get, but getting the concept down and just thinking about it mathematically is very helpful. So let's transpose our velocity versus time graph to an acceleration versus time graph, and let me keep it consistent with the y-axis. So here we see time and then acceleration, right? So since we get this, since we now know that the slope of the velocity versus time graph is the acceleration. So we see our acceleration is constant. So just like our velocity versus time graph last time, our acceleration is just going to be a straight line because this is just a constant line, right? And this is essentially showing us that the velocity is always never going to change. And now this is going to help me demonstrate my previous point. So we also remember that the velocity or the change in velocity was this kinematics equation, right? Not change in velocity, sorry. Just velocity, final velocity was, or actually, yeah, change in velocity, right? Change in velocity was a times t, right? Or acceleration times time. Again here, let's see, if we were to find the area under this line, right, we would get this side length would be whatever our acceleration is, and this side length is whatever our t is. So area of a triangle would be at. So again, we are seeing that the area under this curve right here, let me get a different color. So this area right here is actually our change in velocity. So again, all these graphs are related, as we can see. So that means this is our change in velocity, right? And again, here in the top case, right, where we had a 0 acceleration, we don't have an area, so that just means it's 0, and that's because our velocity never changed. So there is no change in velocity. So as we can see, these graphs are all completely related to each other, right? And they all build on top of each other. So we saw that increasing displacement, and then we saw constant displacement, and they all really just tie back to our kinematics equations. And here again, in acceleration case, we saw that it had a constant acceleration, right? And on AP Physics 1, you might not see cases where your acceleration isn't constant because that's going to require more calculus. But if you do, just like something like that, right? Increasing acceleration, we know that since it's increasingly accelerating, that means our velocity can have like this curved shape to it, right? Like we saw here. So there's patterns to these graphs. So when you're having increasingly something else, you're gonna have graph's probably gonna be a curve, and then the next graph following it in the line will be a straight line or a constant, and then after that it will just be a straight line, right? Constant, right? Like that. So there are patterns to it. So So I think now we can get onto our practice problem, and when we go onto our practice problem, it's going to make a lot of sense. So let's get to that. All right, so here's our practice problem, and so here we see there's some some person has gas that's driving through the town with 25 meters per second, so that's our initial velocity, and then it began to accelerate at a constant rate. So this is our constant acceleration, and they're actually accelerating the negative direction. I'll talk about what that actually means. So, and then it says they eventually come to a stop. So first we want to represent a graph of velocity versus time graph and use that to determine the displacement and or distance traveled. And the second one just wants us to prove if that's actually the right way of doing it. So let's first talk about this. So we have an initial velocity of 25 meters per second, right? And where acceleration is negative 1 meters per second squared. So that just means, the negative just means they're accelerating in the opposite direction. So this is actually going to be a small concept here. So there's this thing where if your velocity is increasing and your acceleration is increasing, that means you're speeding up, and that makes sense, right? Because when we're speeding up in a certain direction and then our acceleration is also in that direction, that means we're just going really fast. But in other cases where your velocity is in a certain direction and your acceleration is in the opposite direction, that means you're slowing down, because again, our velocity is, or our acceleration is the rate, is change in velocity over time, right? Or we can think about it as our velocity is how fast or how much we're going in a certain direction, right, over a certain period of time. So that's like our speed, right? So that just means that if you're accelerating in an opposite direction of your velocity, it means you have to be slowing down, right? Let's say I was, like in this example, it's going 25 meters per second to the right, or let's say that was my reference frames to the right, and their acceleration, however, is the opposite direction. That means they're slowing down. So that it's opposing their motion of, like, their acceleration is opposite to the motion of their object, so that means they must be slowing down. So knowing that, what we see here is a case where the car is actually moving at a speed 25 meters per second in a certain direction, but they're slowing down at 1 meters per second squared. So what that means is, since we know our since we know our acceleration is displacement over time, right? So then we also know that acceleration times time is our change in velocity, right? So since we go from 25 to 0, change in velocity is actually v final minus v initial, right? And we found that out last time, so a times t, again here. And since we want to find out time, right, because we're trying to get a velocity versus time graph, so if we don't know the time, it's going to be kind of hard to do. So this is just, our time is just going to be velocity of final minus velocity of initial over acceleration. Now we know that, we see that it says that it came to a complete stop. So what that really means is that the final velocity is actually 0 meters per second, because they're not moving. So you can't really not be moving and then be at a stop, right? Or you can't have velocity and just be at a stop, right, in this case. So that just means that our change in velocity is actually 0 minus 25, which is a negative number, negative 25. And then our acceleration was already negative 1. So our time is just 25 seconds. And now that helps us. So I'm just going to write it down here. So, I'm just going to write it down here. So time is 25 seconds, right? That's how long it takes for them to come to a stop. So let's draw a graph here. So if we were to draw a graph, and this is going to be sort of a, hopefully a neat graph, right? So velocity versus time, and then so we have velocity and then time here, and then velocity here. Velocity here. And I'm just going to label it out by 5s just to keep it simple. So for my time, so 20 and 25, and then our initial velocity was 25 meters per second. So 15, 20, and then 25. Okay. So what we see is that initially we're here, and then at the end at 25 seconds we're at 0. Now, key word here is we see constant rate. So that means our velocity our acceleration is constant. And if you recall from our previous, when we were talking about acceleration, if our acceleration is constant, meaning that it's just our acceleration versus time, this is a quick drawing, our acceleration versus time graph, constant meaning this. So that means our velocity must be a straight line, or changing constantly, right? So that means if I can draw this well, this is going to be a straight line. It's close enough, right? And then so that means our velocity is, this is our velocity versus time graph, right? because we started at 25 meters per second and then we ended at 0 at 25 seconds, and we constantly accelerated and slowed down, right? So that's essentially the first question done, right? That's our velocity versus time graph. Now we want to determine the distance, and as we talked about it, it's just the area under the curve. So now here we actually have a triangle. So recall quickly, area of a triangle, 1/2 base times height, right? So our base here is 25, and then our height is also 25. So it's just going to be 1/2 25 times 25, and which is essentially that's essentially just 312.5, or we can just round that to 313 meters, right? That's how much distance they cover. Now they want us to actually, in the second part of it, they want us to confirm, in fact, I'm erasing the time, but I'll just rewrite it here. And now they want us to confirm that using the kinematics equations, that we can find that this is the actual distance. So what I'm going to do is I'm going to use the third, or v final squared is equal to v initial squared plus 2 times acceleration over displacement, and this is what I'm going to use to find our displacement. So our displacement is just essentially v final squared minus v initial squared over 2 times acceleration, and so that's essentially going to be 0 squared minus 25 squared over 2 times -1. And if you think about it, right, our 1/2 times base times height is essentially the same thing here, because what we're going to get now is just 25 squared over -2, or 25 squared over 2, which is essentially the same thing that we have here, 25 squared times 0.5. So that means our displacement is also going to be the exact same thing. So that's just proving the point. So I hope you liked this video. This was just going over graphs, and graphs are going to be pretty important in kinematics. And so again, I hope you liked the video as I stated. Please like, share, and subscribe, and I hope to see you soon.